instead of the warm-up, I want us to work on quizzes today, if we have time after the lesson, which we should. So, today we're doing section 15.9, which is on Jacobians. Jacobians, of course, are named after this mathematician, Carl Gustav Jacob Jacobi. It's pronounced in different people pronounce Jacobi in different ways. I've always just said Jacobi. I'm sure there's other ways to say it. Carl Jacobi was the first Jewish mathematician to be appointed as a professor in a German university. Born in Potsdam in 1804, he was home taught by his uncle and advanced quickly when he transferred to a gymnasium. A gymnasium is a name for an advanced German high school. All right. He was a senior by the time he was 12, but he had to wait until he was 16 before he was allowed to attend Berlin University. Most of the math offered there was too low for him, so he self-studied Euler, Lagrange, and Laplace.
Self-studying in the 1800s must have been brutal.
Oh, yeah, I bet it was a little bit harder than today, yes. He earned his doctorate in 1825 with a dissertation on partial fraction decomposition, right? Okay. All right. It's fun reading about mathematicians whose dissertations are on things that like we know, understand, and can do, right? Not on current mathematicians whose dissertations I can hardly even pronounce the words in the title. So anyway. By 1827, he was a professor, and by 1829, he was tenured at Königsberg University. You guys don't know why Königsberg is famous?
Seven bridges.
Seven bridges of Königsberg problem, yes. Okay. Where he stayed until 1842, he was extremely overworked and suffered a breakdown in 1843, which spurred him to move back to Berlin. However, he died of smallpox in 1851. He never married. I'm not going to make any comment why. I'm sure he was a great guy. Poor guy. He never married. He never had any children, but he gave us Jacobians. Okay. All right. So today we are learning how to do U substitution in multiple variables. So when you do a U substitution, and in our case now we're going to do like a UV substitution. Later on we might even do a UVW substitution, right? So anyway, when you do a U substitution in multiple variables, when you do U substitution in a single variable, one of the things you do is you set U equal to stuff in terms of X, right? And then the next thing you do is you differentiate, you find du in terms of your dx, right? Well, what happens if you have u's in terms of x's and v's in terms of y's, and you have a dx and a dy? How do you replace it? You can't just stick stuff on and multiply it together. Math doesn't work that way. So what Jacobi figured out was how to replace the differential part of the integral when you do multivariable substitution. So anyway, so what he did was he figured out how to convert dy dx to dv du. So it's the Jacobian doesn't do the whole substitution for you. All it does is it replaces your differential part, the dy dx, with whatever your new variables are. All right, so where's my little let me get this out of the way. It won't move over. Oh, here, wait, maybe it's gonna, that's weird. Okay. All right, can I make this go down? Well, I'm pulling it. How can I resize? It's not letting me resize. I'm just gonna deal with it. Okay. All right, whoa, whoo, I don't want that. Something weird is going on with my screen. All right. Okay, so we talked about that. All right, so if x equals some function in terms of u and v, and y equals some function in terms of u and v, then the Jacobian of x and y with respect to u and v, it's denoted with your partial symbols, and it's partial xy over partial uv. So it's like dxy duv. So this becomes, anyway, this is the Jacobian, and this is what you're going to multiply by your dv du, or du dv, depending on what order you put it. All right, so how do you calculate the Jacobian? It's the determinant of the matrix of partial derivatives. So what you do is you've got x in terms of u of v, you've got y in terms of u and v, and you find dx du, dx dv, dy du, dy dv, and you do the matrix, the determinant of the matrix. So multiply down, subtract, multiply up. That gives you what's called the Jacobian. The Jacobian can be anything. It can be a number, it can be a function. It all depends on what those partial derivatives are. So normally, if we do a double integral to find area, we have no integrand. But when we convert our variables from x's and y's to u's and v's, we are now going to have whatever the integrand of whatever the Jacobian is. The Jacobian becomes your new integrand. If for some reason I thought it was time to be evil and made you do this with 3-variable conversion, then you would do the exact same thing and you'd have a 3-by-3 matrix, and it's still the determinant of the 3-by-3 matrix of partials. Does everyone have down like how to calculate the Jacobian? Okay, read it in a minute. I really feel like going and getting my winter coat off my desk.
Just do it.
It's okay. I'll be okay. It's okay. You guys are almost done anyway. You're not writing every single word, are you? Okay. All good? And are you okay?
Yes.
That's okay. Just make sure. All right. Okay. So we're going to start by an example. So up here, this is just rewriting what you just saw on the last slide. So you don't rewrite it again. It's the exact same thing. All it's, whoops. Okay, let me move this up, all it's saying, so if you have, if you want to find area, or if you say you have a double integral, and even if there's a function here, right? So if it's maybe like a volume double integral or some double integral with an integrand, then you can still use the Jacobian. You just have, like when you convert your limits to u's and v's, but you also have to convert your function to u's and v's, and it's still just times the Jacobian times du dv or dv du, depending on which way you're going. Okay. All right. That's me saying if you want to prove. I deleted that because it's not on page 1044 in your textbook anymore because that was the old book. And I'm sure I deleted this line, but I guess not allowed. Here. Let's delete. We'll just delete right here on the spot. Okay. All right. There we go. This note's important. Whenever you're using a Jacobian, you always have to use the absolute value. So if you use a Jacobian when you're processing an integral, it has to be the absolute value of whatever you get. Because the Jacobian, depending on how you arrange things, how you choose your u's and your v's and what order you pick them in. The Jacobian can be either positive or negative. You always pick the positive. You're always going to use the positive Jacobian. Yes?
So you do the absolute value of the Jacobian or the absolute value of whatever you get after you use the Jacobian in the equation?
The result of this is called the Jacobian, and this has to be absolute value.
Okay.
All right, are we ready to try one? Okay. All right. Most often, you will see UV substitution on when you have to do areas of spaces that would be a real pain in the butt to do in terms of X and Y. Like if you look at this little, I don't know if it's a square or whatever, parallelogram or whatever it is, but it's definitely a parallelogram for sure. If I do this in terms of X and Y, I'd have to split this into like 3 integrals, right? So it'd be such a pain in the, no matter which way you do it, you're gonna have to split it. So because it's such a pain in the butt to have to split into all these multiple integrals, sometimes it's easier just change your variables. So that's what we're gonna do here. We're gonna, and just, you know, some of you have been asking me on your test, do I say like use cylindrical or use spherical or whatever? I don't. However, I do on the Jacobian problem say use the Jacobian. So on the Jacobian problem, I'll tell you, and I want to see you change the variables. So it's really just to check to make sure you can change your variables. All right, so R is the region bounded by x minus 2y equals 0, x minus 2y equals negative 4, x plus y equals 4, and x plus y equals 1. A little warning about your homework tonight, because I did take a look at your homework tonight. Bless you. If your book or if the problem is presented in traditional like y equals mx plus b form, like solved for y, so if you have like y equals, in this case, like y equals 1/2 x, y equals whatever, 1/2 x plus 4, like that kind of stuff, right? Whatever it is. Your life is so much easier when you're doing these if you write them in what's called standard form. So if you rewrite your equations in standard form is ax plus by equals c, you're gonna, it just makes everything easier. So just a little note for you guys. So if it's presented in slope-intercept, rewrite it in standard form, and then you'll be looking exactly like this. Okay. There's not a lot where you actually have to do it tonight. A lot of it is just kind of matching and looking at stuff. So anyway, all right. So we're going to evaluate the double integral over that region of 3xy. So this could be a z function, could be z equals 3xy, and we're finding value, right? But anyway, so we're going to evaluate this double integral. The first thing you have to do is pick what do you want u to be and what do you want v to be. For the problems that you will be given, and it can be done with other problems, but just because we are kind, and this is true in the homework as well, you're only going to be given problems that involve parallelograms. It's just later on we could do substitution with other functions, but right now you're only given parallelograms, which is why it's easiest if you write them in standard form, because then these, you'll have 2 that match, and you'll have another 2 that match, and just let one of them be u and one of them be v. So you let your u, like I have u equals x minus 2y and v equals x plus y. Life doesn't always work that way, but in this class it's going to this semester. Okay. All right. Okay, here's the part that makes them fun. You have to solve for x so that x is only in terms of u and v, and you have to solve for y so that y is only in terms of u and v. The only part of the Jacobians that is tricky is the algebra of solving for x in terms of u and v and solving for y in terms of u and v. So I'm going to tell you, so we have this guy, right? So the first thing that I do personally is I go ahead and I would solve this for x first. So I'd have x equals u plus 2y. So go ahead and solve this for x. You get x equals u plus 2y. And then if you solve this for y, you get y equals v minus x. Once you do that, just take one of the variables, like this y, and substitute it into your other function. You should end up with an equation that you can solve for x then. And it will, the answers would be in terms of u and v. And then once you get your x, then you substitute that into the x over here, and you can get your y. So everyone, I want you to see if you can take a minute, find x in terms of u and v and y in terms of u and v. All right, so I replaced my y with v minus x, and then distribute the two, solve for x. So then you got to divide by 3. So x equals 1/3 times u plus 2v, the quantity. You can distribute the third. I don't care. That's fine. Potato, potato. I've been saying potato, potato a lot lately. Okay. Now you got to find y. So what you're going to do is you're going to take this guy and plug it in for the x in your y equation, right? Okay. So you do that, a little more algebra, magic, and you end up with 1/3 times v minus u, right? Or 1/3 v minus 1/3 u. Talk to me about solving for x and y in terms of u and v. Are we good? Why are we doing this? Because you're going to have to replace all your x's and y's with u's and v's. So it's good to know what x is and what y is, right? Okay. All right. Good. So we got that. Now we have to find the Jacobian because we want to rewrite this. We got to rewrite this whole integral. So now we can replace the x, we can replace the y, but we still have to replace the dy dx or dx dy, whatever we're doing. So we need to find the Jacobian. So you have your x. Where's my x? Oh, here. Okay. So I'm going to put a new box around my x. Okay, so there's my x. And then there's my y. So remember, the Jacobian is the determinant of the matrix of partials. So you make a matrix that's dx du, dx dv, dy du, dy dv, right? So go ahead and make a matrix of, oh, I don't want you to see it. I'll go this way. So make a matrix of partials, dx du, dx dv, dy du, dy dv, and actually find them. Put them into the matrix. So find like dx du, what's dx du? 1/3, right? So pretty straightforward. Go ahead and see if you can figure out your matrix of partials. All right, did everyone find the Jacobian? Do the determinants. I got positive 1/3. If you got a negative 1/3, that's okay. You just have to make it positive. Did you really get it right? Oh.
I can't multiply.
Yeah, it's okay.
When I'm trying to multiply 3s, I
Okay,
don't know why.
are you okay? Ryan, how you doing? You got it? Good. No questions? Okay. All right. So we found our x in terms of u of v, we found our y in terms of u and v, and we found our Jacobian. It's time to rewrite the integral. This is the part I think you're going to like more than you think you're going to like it. Okay? All right. So the most fun part of rewriting the integral is finding the new limits. And then we're going to talk about the new graph in a minute. But the most fun part is finding the new limits, right? Okay. Look carefully. If this is your equation, x minus 2y equals 0, and you've now just called it u is going from 0, or you have u equals 0, u equals -4. Those are your new u limits, -4 to 0. If this is your v is going 1 to 4.
Oh.
Yeah. Isn't that nice? I know.
Everything.
I know. So since this is u is going from -4 to 0. Since this is v and this is v is going from 1 to 4. It doesn't matter because they're all numeric, so it makes no difference if you go dv du or du dv. As long as you have the right numbers with the right variables. All right, so you've got your limits, then your integrand, which is normally 3xy, you have to replace the x with what it is, which is this guy, 1/3 times u plus 2v, and you have to replace the y with what it is, which is 1/3 times v minus u. Okay. So your new integral, so we found our limits. Now we rewrite the integral. So the integral of 3xy, big partial thing, I'll call it Jacobian. 3xy Jacobian dA. So you have 3 times the new x times the new y. I don't know why I didn't fill in the Jacobian right here, but that would be our 1/3 dA. Putting in the limits. So you get, this is our, oh, no, that's just me pulling up all of this stuff out and cleaning up in one step. So anyway, so your limits, -4 to 0 and 1 to 4 of your 3xy, which this whole big thing, including the 1/3, that's equal to your 3xy. And then that's your Jacobian right there. That's your Jacobian. And then dv du. So that's me just cleaning it all up.
Wait, so we have to like also multiply them.
All your integral is all, like the whole point of converting the dx dy to a du dv is dx dy or dy dx is equal to Jacobian times du dv. So when you rewrite your dx dy or dy dx, you will replace it with Jacobian times du dv or dv du.
So you don't pull up the Jacobian and put it before the integral, right?
You can, if it's numeric. It won't always be numeric.
But how come you didn't do it like in the first?
I don't know, because I was being stupid. I would have, like, if I was doing this now and retyping, I would have just put it right there.
Okay.
I don't know why I did
Okay.
this. Yeah. So honestly, I would have, like, if I was redoing this, I would have gone ahead and put my limits on that first step too. I don't know why I didn't. Zach, I can't tell.
I get it, I feel like I made a mistake. It's simple.
Yeah, there's a lot of algebra and a lot of calculations. Yep. There's what? Oh. Did you just ask me what 4 times 4 is?
It's in my head.
Oh, okay. Did you finish this? Yeah, actually do it.
Alright.
All right, after cleaning it all up and doing the first integral, I integrated with respect to v first, so because I did dv/du. If you did it backwards, you did something different. So that's me. Plug in the 4 minus plug in the 1, and it cleans up to this guy. 1/9 integral -4 to 0, 42 minus 3u squared minus 15 halves u. Is that what you got? Okay. And then,
Wait, what?
and then integrating with respect to u, got that plugged in the 0 minus plugged in the -4.
Like 32.
Alright.
Oh,
I missed everything.
did you get it? My mistake?
Yeah.
Okay. Lily, how'd you do?
At the beginning, there's 3 and 1/3.
So
And those 2 cancel.
this 3 and this 3rd cancel, but I have another 3rd here and another 3rd here, right?
The last 3rd.
That's the Jacobian.
Oh.
Did you not multiply by your Jacobian? That's really important.
Is the Jacobian always like the same as?
No. A lot of times the Jacobian can be a function.
This is like a weird one to do your first time because you don't notice. It's hard
Yes,
to
Jack.
tell.
Yeah, so it's kind of like doing a u substitution for a single integral. We're baby stepping into it. When you know how there are some single integrals that we can't evaluate because there's like guts in, it would have required like chain rule. U substitution is kind of like undoing chain rule. Well, when you're in multiple variables, you need to be able to have that same opportunity to be able to undo chain rule with multiple variables. So now, instead of u substitution, we're doing u to v substitution. We're substituting both variables out. When you substitute traditionally, you do a u equals, and then you find your du, and you replace your dx with whatever you get with your du. Does that ring a bell?
Yeah.
Okay. So when you have multiple variables, you have a dy dx. You can't just replace them with a du and a dv. It doesn't work that way. It's not like it's this integral time or this derivative times this derivative. There's more to it in that, and that's what Jacobi figured out. He said if we need to replace the differentials in a multivariable substitution, what do we have to do to replace them? And that's what the Jacobian gives us. The Jacobian allows us to replace the differentials when we're doing a multivariable substitution.
And then so how do we know when to use it? Do we like
Anytime you substitute variables in a multivariable integral.
You just do it like whenever you want.
Yeah, I mean, just like you substitution, you can do whatever you want, you know.
would
Okay.
we like start a double integral and be like, oh, I can't do this, and then do something?
That could happen, but on your test, I only put 1, and I tell you use the Jacobian, so it's not like it's a big mystery. But yeah. Okay. One other thing I need to talk about is the graph, because there's a lot of this in your homework where they say something like, pick which graph would be the image of this integral based on the Jacobian. So image just means the new graph. That's all it means, right? So we went from this graph in the xy coordinate plane to this graph in the UV coordinate plane. Much nicer graph, right? So how do we get from this graph to this graph? Well, if our u's and v's are equal to constants, then it's really easy. I mean, you just look for the rectangle with the correct constants, right? So if the u's and v's are equal to constants, it's really easy. Even if they're not, as long as you've got something where u equals something and v equals something, when you define your u in terms of x and y, you can take a given vertex on your xy graph, plug in the x and y in to your u function, and that gives you your new u value. I don't know how to say that well, right? You do that for each of your vertices, and you do it for both, for each vertex, you do it for a u and you do it for a v, and you'll get the new corresponding vertex on the new function. I'll show you later. That's not a part. It's in your homework. It's easy. My words aren't doing it justice. It literally is something you'll go, oh, and you'll get it in 2 seconds. So anyway, okay, all right. I'm gonna move this up. There we go.
Can we do it on the board?
You want to do this on the board? It's a lot of writing to do on whiteboards.
Yeah, but I don't really use another full page with your notes.
Oh, okay. All right, so let R be the region bounded by the square. It's going to be a tilted square with vertices 0, 1, 1, 2, 2, 1, and 1, 0. Evaluate the integral x plus y squared sine squared x minus y dA over the region of that square. So you're going to have to find u, find v, rewrite x in terms of u and v, rewrite y in terms of u and v, find the Jacobian, rewrite the integral, and evaluate. You can do this. All right. Okay. All right. So, where's my picture? I don't have a picture. All right. So, 0, 1, 1, 1, 2, 2, 1, 1, 0. All right. You get that guy right there, right? And so you had to figure out all of your equations, which apparently I thought I had on here, but I didn't. So this one's not bad. This is just y equals x plus 1. This is y equals negative x plus 1. This is y equals x minus 1. And this is y equals negative x plus 3. All right, so there's my 4 equations. So you have to write them in standard form. So I had x plus y equals 3, x plus y equals 1. Let's see, y minus x, you do y minus x equals 1, and y minus x equals negative 1. Okay. Now, different answers arise, not final answers, but in the middle, different answers arise depending on how you solve your equations, right? How do you write them in standard form? Are you, did you do y minus x? Did you write it as x minus y equals 1, right? So different ways, depending on how you write your equations, cause different u's and v's to arise and cause the middle of the problem to be different based on how you chose your u's and your v's. That's okay. You'll always end up with the same answer if you do all the math correctly. So, see, and look at this. Like when I did this the first time, I did it backwards. So I did x minus y equals negative 1, x minus y equals 1. So I let u equal x plus y and v equal x minus y. Rewriting, solving for x equals u minus y equals x minus v. Then you take this y, plug it in here, you get u minus x plus v, and then you add the x over, and you end up with 1/2 times u plus v. So there's my x. And then my y, I got 1/2 times u minus v. All right, your x and my y's might be slightly different, slightly rearranged, but they should be somewhat similar to those. So, like this one has 1/2 u plus v and 1/2 v minus u. Still fine. It just depends on how you wrote your equations. Okay? That's what makes grading these really fun. Yeah. So, all right. So you get that. Then you need to find your Jacobian, right? So I got a Jacobian based on mine. I got -1/2. When I write it in my integral, I'm going to put it in positive. Does that make sense? Okay. All right. Good. So now let's rewrite our integral. So our limits, my limits for u are going to be 1 to 3, and my limits for v are going to be -1 to 1. Okay. And then I got to replace all my x's and y's with all the u's and v's. That's just me talking about the limits. Okay. All right. So here's my integral. So I have x plus y equals u. That's nice. X minus y is v. So I just have u squared sine squared v times my Jacobian du dv. Piece of cake. All right. So when I integrate with respect to u, I just get a 1/3 u cubed, and I plug in the 3 minus plug in the 1, and I end up with 26/3 sine squared. I'm not lying when I say I don't remember if there are any double angle for like where you have to do power reduction identity on your test. You really should know those. So power reduction for sine, if I have sine squared v, so that's 1/2 times 1 minus cosine 2v. Right? And then cosine squared is the exact same thing with a plus. All right, so I rewrite, that's as far down as it goes. So I did 1/2 times 26/3, called it 13/3, and then rewrote my sine squared as 1/2 times 1 minus cosine 2v. Then you can anti-differentiate. Just remember, the antiderivative one is v. The antiderivative of cosine 2v is sine 2v divided by 2. You always got to divide by your slope. Does that ring a bell? Or do a u sub, right? But you wouldn't do a u sub, though. You'd do like a q sub. Okay. All right. So anyway, plug in the 1, plug in the -1, and okay. So 1 minus 1/2 sine 2 plus 1 plus 1/2 sine -2. So here's the thing. Sine is odd. Sine is an odd function. Not odd unusual, odd literally odd. Sine is an odd function, has origin symmetry, right? All odd functions, whenever you have an odd function, it means f of -x equals -f of x. So sine of -2 equals negative sine of 2. So I don't know why I didn't combine the like terms though. So I get 13/6 times 2 minus sine 2. Which should be, now if you kept your sign like with the -2, that's fine. But I don't really care. So anyway, so either way, if it's equivalent to any of these, it's fine.
So let's go.
So did you get it?
No, I didn't check it. Did I check it?
Yes, you should check it.
That's exactly Okay.
How are we feeling about the the general process of Jacobians? Danny's nodding like he likes it. Is that the, you're asking me if that's the same?
If you did plus,
let's see. Yeah, you distributed the 13/6 in. Yes. Yeah. So plus sine -2 is the same as minus sine 2. Yeah. Yep. Very good. You got it. Well done. All right. Good. There are a lot of places to go wrong. You have to be very clean and neat and methodical. Yes. Okay. Whoa, whoa. You're going to like this next screen. Oh, okay. Okay. Questions? Sujesh, you have questions?
I'm just confused as to why I got sine 6.
Yeah, we're
Tell me where your work became different.
It was different from the beginning.
I got it right. Let's go.
You got it right? Way to go! So we had quite a few words that got it right.
Oh, never mind.
Yes,
I figured it
sir.
out.
Did you?
Yeah.
It looks right.
I just can't do math today for some reason.
Every
Yeah, exactly. I can't do math. I need it.
All right. So just wait. I want to hear. Wait. Don't look. Where's my escape? Escape. Escape.
You got it right.
Okay. Okay. Just for fun. Quiet, please.
Oh no.
Just for fun. This is already solved for x in terms of r and theta and y in terms of r and theta. I want you to find the Jacobian for x equals r cosine theta and y equals r sine theta. So dx dr, dx d theta, dy dr, dy d theta. Find the Jacobian. Take a second.
All right. Yeah.
You know how to just do it on paper? It literally takes a second. Okay, all right, boards. All right, so the Jacobian of r cosine theta and r sine theta ends up just equaling r, which is why when you switch from x and y to r and theta, you have to multiply your differential by r. So because r is the value. That's one reason why. There's a bunch of mathematical reasons why, but this is just more evidence of why. The other thing that we could do, it takes a few minutes though. If you're ever bored, what you could do this is you could find the Jacobian for x equals r cosine theta sine phi, y equals r sine theta sine phi, z equals r cosine phi. Because if you do the Jacobian for your spherical conversion, what do you think you're going to get? Rho squared sine phi, right? You're going to end up with the thing that we have to multiply the d, I can't even say it now, d, rho d phi d theta, right? Yeah. Okay. So anyway. All right, I did this once. It took like a sheet of paper. It's kind of fun though, right? And it works. So anyway, all right, so that's it. That's all I want to do with Jacobians today, except